temperature, pressure, etc. are all fixed. So the whole system is in thermal equilibrium. But you have decided to drop a ball. You can have water or a liquid. I mean, this experiment is done in the IISc Kolkata undergraduate laboratory. This ball has a mass n, has a radius r, etc. So this r is different from this r, so let me call it a. And it goes down due to gravity, right? The force of mg, m, students can measure it. You can measure the radius by a vernier caliper or something. So the volume, the radius is a, so the volume is 4 pi a cube. And assuming that you know the density of the material, then you know the mass. So there's a force going down. But this force will be opposed by what is called the force of buoyancy. That's simple to calculate because that force of buoyancy is the weight of the displaced liquid. The weight of the displaced liquid is just the density of the liquid times the volume of the displaced amount. The volume of the displaced water, according to Mr. Archimedes, is the same as the volume of the ball. And so you will get another term which will be here, when you have a density of the ball minus the density of the liquid, that will be an effective force. But more importantly, the ball as it goes down suffers collisions from the surrounding particles. And these are water molecules. And that's what Robert Brown saw, not in terms of a ball going down, but pollen particles in the water, right, under a microscope that he designed himself. And this is now already almost 200 years old. Okay, that experiment. And so what Brown said, well, he didn't say it, Einstein explained it, that this ball suffers more collisions from the front than from the back. So there's a net retardation force, and that retardation force is sometimes called a frictional force. Or frictional force. And that's assumed by a gentleman called Stokes is to be proportional to the velocity itself. So it's in fact has a form of minus 6 pi eta times the radius times the velocity. So you see, this term is like your m over tau term occurring in the Drude model of electrical conduction. So the idea is very similar. Here also, as you know, to have this picture implementable or satisfied, the ball must have a size much bigger than the surrounding particles. Similarly here, the role of the ball is in fact that of the electron, and the electron is already somewhat bigger than the other excitations that occur in the system. I mean, phonons, of course, are just excitations, quantum excitations are quasi-particles. But so that's the picture, that you have a term which goes like m over tau. Hence, so this is the simplest idea of Einstein when he talked about diffusion, right? So because now this is called a Langevin equation, and if you put in noise, then you have a model for diffusion, right? And Einstein used that model, right, to calculate things like diffusion coefficient, etc. Because his idea was to calculate the Avogadro number. So anyway, so that's part of history. So how does one make this Langevin equation a noisy equation? You put in explicit noise sources. Where does this noise come about? The noise is actually there in the surrounding medium. The noise is happening because I have a temperature, and therefore each of these red particles, the balls, are actually moving randomly in the medium. Their average kinetic energy is given by Heat partition theory. So the experiment that is carried out here is to write down the equation of motion with this Stokes frictional term, and then wait until this ball acquires what's called a terminal velocity, because see, if you have a force going down like this, and the force opposing this, ultimately, and since this force is velocity dependent, the ball will acquire a certain velocity when these two forces will match. When they match it, absolutely. So so these are the details that you have to worry about, because what Dr. Mitra pointed out, let's see, when you're talking about fermions, remember the fermions have statistics, right, called fermionic statistics, where you have all learned in the elementary statistical mechanics that the occupation probability of fermions is a step. So at t equal to 0, this is the way it looks like, because f of e is equal to 1 over e to the power epsilon minus mu over kbt plus 1, right? And at t equal to 0, mu is what is called the Fermi energy. The chemical potential is the same as the Fermi energy. And so all states up till EF are occupied, all states beyond EF are unoccupied. And therefore, as you pointed out, that you say that there's a Fermi sphere in the energy space where you can think of a Fermi momentum. So Pf squared over 2n would be Ef. That's the way you define the momentum. And all states within the Fermi sphere are occupied, right? Now, if you want to have transport, then of course you cannot have any transport because all states are occupied and there's nothing, no elbow room for the electrons, so to say. So you have to actually change the temperature. And if you change the temperature, then the Fermi distribution will start looking very similar to this, but then you'll have like this factor. So you will therefore have possibilities of these electrons going beyond the Fermi sphere, and they are the ones who will participate in all kinds of transport processes. Not just transport, specific heat. You know how to, this interview question, that how do you get the specific heat of electrons, all right? The specific heat has a very characteristic temperature dependence. What is that for fermions, for electrons at low temperature? It's an interview question that we always ask. That the specific, what happens to the specific heat for a classical ideal gas? What's the specific heat?
Constant.
It's constant, right? Because you have this Dulong pit, the energy goes linearly as temperature, and so when you do this equipartition theorem, and when you do the derivative, you get a constant. But then as you go down in temperature, what happens?
TQ.
First TQ happens due to the phonon contribution. Because phonons are like bosons, so that's TQ. If you go to further down in temperature, T, precisely. So why? So CV is proportional to T. So when you say that, the number of electrons which participate in anything, in this case it is heat transport. Specific heat is a measure of heat transport. Then the fraction of that number is kBT over EF, and then make a statement that, well, these things are loosely bound electrons, so they're like classical particles, so each will contribute an outside energy kBT, so you get a factor of T squared. When you take a derivative, you get T. So that's the characteristic linear specific heat temperature. So not just specific heat, any kind of transport, conductivity, etc., will therefore, the relevant electrons would be like the shaded area electrons. And that's what Dr. Mitra said, that they are actually moving with a Fermi velocity BF. So think when you bring in the Fermi sphere, Fermi statistics, etc., you have to have a clear idea of what velocity you're talking about. Okay? That's the point that we. All right. But, so as I said, today we're not going to visit all the research areas of great interest, that actually when you bring in the external bath and see how these terms come about by averaging over these bath excitations, and you get what is called a quantum Langevin equation. This is a subject of current interest, and because of these dissipative terms, if those terms were not there, the motion is quantum mechanically coherent. But if you have dissipation, then you have incoherent effects. So coherent, incoherent transitions also are of great importance today, and in fact contextually important also in the context of computing, quantum computing, etc., etc. So there's a lot of masala here and areas of interest for research. Okay, so now coming back to this, our simple-minded model is like a tight binding model where we have site energies and then possibilities of hopping from site to site. So this thing then has to be juxtaposed onto a lattice model where electrons can move from one side to the other, and if the motion is facilitated, then you will say that it's like a good conductor. Okay? One of the things that becomes very important is that if you start bringing in disorder into the system, due to defects. Now the disorder can be in this term or in that term. So this is what will give rise to what's called site disorder, and this will give you hopping disorder. So either of these cases, suppose there is no hopping disorder, you put in a site disorder, and that is the famous Anderson model, written down by P.W. Anderson in 1958. So you think of that epsilon has L as actually a certain distribution. For instance, it can have a Gaussian distribution, a probability of lots of epsilons. Like in the Maxwellian gas, you say, I don't know what velocity actually is. All I can say is that I have a Gaussian. So you can think of a Gaussian, for instance, and introduce a parameter which is the width of this distribution. So that becomes an important parameter, width of the disorder. And if this hopping is a constant t, then you in fact have a parameter in the problem which you have to worry about, and that's what Anderson did, is to have a parameter called t over w. There's a new parameter in the problem which you can define as t over w. So it's Anderson 1958. I mean, his citation and Nobel Prize also, which he shared with two other great physicists, Van Vleck and Neville Mott, cites his work also on localization. So that's the Anderson model. We'll come back to that later. Now, so there's some buzzwords are there in the literature that you see. I told you that this problem is very similar to the problem of diffusion. So actually Anderson's paper, okay, now let me say what the paper title was. He says, absence of diffusion in a lattice. Okay? Why is he calling absence of diffusion? Because he proved that if there is disorder like of this, then if the disorder is large, the W is large, then there is a transition for a sufficiently small value of T over W where you go from delocalized states to localized states, and that's called the metal insulator transition. A very important problem today, that you keep on increasing the disorder, you have hopping, but suddenly the electrons get localized on one side. They're not able to hop. And then there's a transition. It's also called the Mott transition, or the metal insulator transition. And so these things also come in transport properties of materials, especially nanomaterials. So metal insulator transition. And the ideas of diffusion.
So actually, Jacob has left some paper.
greatest happy birthday. Some classified topic. Okay, so see, a language little loosely of diffusion or Brownian motion is used also in the context of electronic transport. But you must realize that electronic transport is a quantum mechanical phenomenon. It's quantum mechanics, there's statistics, okay? But you can still say that, what does diffuse? Actually, it's like wave packet diffusing. And you use the analogy. And therefore, you write conductivity, transport. See, conductivity sigma is a measure of transport, a measure of mobility, like in the diffusion problem. So conductivity then is actually like diffusivity. Okay? So the people say, well, conductivity is proportional to diffusion constant. I'll write down one of those formulae. It's called the Kubo formula. And you use the jargon of Brownian motion, but it's quantum Brownian motion. So the electronic transport problem is like a quantum Brownian motion. These are topics of great interest, and I myself have a lot of research interest in this and continue to work on this. But we're not going to go into any detail about this. So, so these ideas come about, and you will find that these concepts, like what is the relationship between the diffusion coefficient and things like mean free path, the wave vector, there has also become dimension dependent. Okay, so the dimensional dependence of these quantities like conductivity, conductance is something that let me quickly go through, and then we'll break for lunch, and then there'll be the last lecture where I, since it's announced, I don't know whether I'll be able to go into it. Something very remarkable conceptually is what's called the Landauer formula. So anyway, so what did we do? Let's see if we have time to do that, and we meet again at 3:30, and that will be the last lecture. So yesterday we wrote these equations down in terms of a matrix, and then we found out that you can rewrite this as the following matrix. Your sigma 0 is your simple Drude conductivity. Is n t squared tau divided by m. It's the same tau that appears here. N is the number density of the electrons, that's number of electrons per unit volume. And of course, E is a charge. So you have sigma naught inverse. The magnetic field divided by N is C minus B over N is C. If you flip into your notes here from yesterday, you'll find this. Right? Current density Jx, Jy is equal to your components of the E field. So the B field has gone into the off-diagonal terms of the conductivity tensor, conductivity matrix, and the Hall geometry is carried out in such a way that you don't look at any transverse current. So the current moves only along the x-axis. There is no Jy, so that is the Hall geometry, Hall bar geometry. So Jy is actually equal to 0. So we manipulated this, and then, in fact, calculated yesterday.